In this video, we are going to discuss about low-cost test bench for EMC testing of stray capacitive coupling that happens from an EMI source, which is the chattering relay to a victim circuit and unstable multivibrator, the LED flasher circuit. So what has sparked our idea initially? We are about to test EMI vulnerability on our LED flasher circuit as the EUT, equipment under test, and we found out that with a casual lab setup, which is the home lab at our dormitory, we can use chattering relay as an EMI source to attack the victim circuit. And so here is the experiment setup. We have the chattering relay as disturbance source, known to be EMI source as well. It then coupled the electrical fast transient signal of its electric field by axing the susceptible circuit, which is the LED flasher, as equipment under test. And one thing to note that two of these equipments are actually fully isolated. They have no shared ground with each other. From the top level view, we have the noise source, capacitive coupled through the stray capacitance that develop between conductor of each side, and then sending the electrical fast transient time varying electric field to the victim circuit. Now let's have a look on our susceptible circuit. Another reason of having this victim circuit is because it possesses a high impedance susceptible node at capacitor charging node and transistor base node. So if we perform Ohm's law of diffusion on the timing resistor, we can know that our component behaves as a multiplier to the current element. So with just a slight current injection occur at a particular node, it will cause a voltage spike in the circuit and having the ALE threshold triggering at the base pin of transistor. So that would cause an abnormal timing in the flasher circuit. So that could be observed very obviously. If we really look into our susceptible circuit, this is how the flasher circuit actually works. So before we step into it, we may have a look on the nodes, the blue circle nodes that are output nodes, which output in a square wave repeatedly switching waveform. And the pink circle nodes are capacitor charging nodes. We can observe the node capacitor charging behavior from this node. First of all, as we power up the flasher circuit, it will run into a race condition between the path. Because the electronic devices used, like the resistors, the transistor, they are not perfectly identical. Thus the current will choose only a desired path to start the operation of the circuit. Like in this case, we have assumed that the last column branch of the circuit won the race condition. So we have the Q1 BC547B base pin holds at 0.7 volt. The collector pins on the other side conducted to ground and holds at a value that is very close to zero reference voltage. Meanwhile, another capacitor C2 on the right side is awaiting to charge until 0.7 volt to make the switching, as we can observe from the waveform on the right side. So as the C2 on the right side is done charging towards 0.7 volt, the Q2 transistor turns on and the output node initially holds at 5 volt will immediately drops close to 0.2 volt as it conducted to ground. In that sense, the opposite pin of capacitor undergo a voltage drop as well. According to the output node, it drops by 4.1 volt. Thus the operation side now flips. In the same behavior, the timing mechanism will work repeatedly and indicating the flashing trend of the LED flasher circuit. So that has summed up our victim circuit, and now we may have a look at our culprit circuit, the disturbance source. So for disturbance EMI source, we set up the relay to act in self-chattering behavior that is constantly performing an automated rapid switching to produce an electrical fast transient signal. Acting at the relay context generates a strong electric field. After that, the parasitic capacitance coupling can occur between two conductors, which are the relay EMI source and the equipment under test, the LED flasher circuit. Because the electric field is time varying, switching rapidly at 0 to 12 volt, at the bottom left corner, there's a real world example I refer from a forum where people measure the EMI noise of chattering relay using oscilloscope as well.
Now I will explain how the electromagnetic interference from the tutoring relay reach our circuit. For the electromagnetic interference to cause any disturbance, it needs a path to go through. This path is called coupling path, and as you can see in the diagram, there are two types, which is the first one is capacitive coupling, where the noise travels through the electrical field between two conductors via a stray capacitance. The second one is the inductive coupling, where the noise travels through the magnetic field between two loops via mutual inductance. In our experiments, the main coupling path is called capacitive coupling. For this slide, we will speak about the mechanism of working for the capacitive coupling. As you can see in the diagram, pattern 1 and pattern 2 are two conductors placed close to each other, even though they are not connected, but a stray capacitance is formed between them, just because of their proximity. When the relay produces a changing voltage Vs, it creates a changing electrical field. This field passes through the stray capacitance and induces a noise voltage Vn on the other side. The equation for the Vn is equal to J omega Rc Vs, and this means the higher the switching frequency of the relay, the stronger the noise voltage that appear in our circuit. Actually, this diagram shows exactly what happened in our experiment. We have our unstable multivibrate circuit, which is the victim circuit. We can also call it the equipment under test. We have the tutoring relay acting as the EMI source. Between them, there is no connection at all, but however, there is a parasitic capacitance exists between them, which act as an invisible coupling path.
This slide shows the susceptible circuit, also known as the victim circuit, before any electromagnetic disturbance is introduced. The victim circuit is an unstable multivibrator which continuously switches between two transistors, causing the two LEDs to flash alternately. This alternating action is controlled by the charging and discharging of capacitors C1 and C2 through resistors R2 and R3. Substituting these values into the equation gives a theoretical frequency of approximately 0.725 Hz. This means the LEDs complete about 0.725 flashing cycles every second. We now observe the actual behavior of the victim circuit under normal conditions, without any electromagnetic disturbance. As shown in the video, the two LEDs flash alternately at a constant and stable rate. This confirms that the stable multivibrator is operating normally. From the recorded video, the measured period is approximately 1.1 seconds. The experimental frequency is calculated as 0.909 Hz. This measured frequency serves as the reference value. Next, we introduce the disturbance source by placing the catchment relay 1.8 centimeters away from the victim circuit. From the video, we can observe that the LEDs flash noticeably faster than the under normal condition. This indicates that electromagnetic disturbance is affecting the timing operation of the circuit. The measured period is approximately 0.18 seconds. The flashing frequency is calculated as 5.556 Hz. The frequency has increased significantly. This confirms that even at a separation distance of 1.8 centimeters, the nearby disturbance is already influencing the victim circuit. So we calculate the percentage increase in the flashing frequency by comparing the normal frequency with the disturbed frequency. The equation gives a 511.22% increase in the flashing frequency. To understand how the capacitor behaves under disturbance, we use the capacitor charging equation. The final capacitor voltage is 5 volts, the initial capacitor voltage is negative 4.5 volts, and the RC time constant is 1 second. Putting these values into the charging equation gives this value, which describes how the capacitor voltage increases over time. During the transistor's on state, the base voltage is capped at approximately 0.7 volts. After the transistor switches off, the capacitor begins charging according to the RC charging equation. The process continues until the capacitor reaches the transistor switching threshold, causing the circuit to change states and repeat the oscillation cycle. This equation represents the normal charging behavior of the stable multivibrator and serves as the reference for comparing how electromagnetic disturbance affects the victim circuit.
This slide explains the premature threshold triggering. Under normal operation, the timing capacitor charges until the transistor reaches its threshold voltages of about 0.7 volts. However, when the chattering relay acts as an EMI source, its time-varying electric field couples into the circuit through parasitic capacitance. As we know the EMT equation, which is Q equal C times V. So extra charge is injected into the capacitor, causing it to reach the threshold earlier. As a result, the transistor switches prematurely, increasing the oscillation frequency. So next, we estimate the minimum stray capacitance required to cause the premature triggering, using the equivalent circuit that we have here and by applying the voltage divider rule. So we calculate an approximate value since professional EMC instruments were unavailable. These values are estimates, but they are sufficient to demonstrate the coupling mechanism and the expected trend. So next we have that the experiment was then repeated by reducing the disturbance from 0.8 centimeter, as we can see in the video here, to 0.4 centimeter. So as the relay moves closer, the electric field becomes stronger, increasing capacitive coupling and causing earlier threshold triggering. And as we can see in the graph here, the larger coupling causes higher oscillation frequency. So the summary table confirms this behavior. As the disturbance, as we can see here, the disturbance distance decreases from 1.8 to 0.4 centimeters, the oscillation frequency increases from 5.556 to 33.33 Hz, showing that stronger coupling produces a greater EMI effect. This table shows the estimated minimum stray capacitance, which is here equal to 10 microfarad. The values were obtained using the equivalent circuit approximation and help us evaluate the circuit susceptibility to EMI. Finally, after increasing the C node from 10 microfarad to 100 microfarads, a much larger stray capacitance is required to produce premature triggering. This means a stronger EMI disturbance is needed, making the circuit less susceptible to electromagnetic interference and improving its EMC performance. So in conclusion, although our capacitance values are approximate, the experiment clearly demonstrates the expected EMT behavior, reducing the distance, strengthening capacitive coupling, and increasing oscillation frequency, while increasing the node capacitance improves the circuit immunity to EMI. Thank you.
And finally, we move to mitigation part. Mitigation is not to change the timing, but to reduce the noise of sensitivity. Mitigation is actually needed because our stable multivibrator circuit is easily affected by electromagnetic interference from the chattering relay. When the relay switches repeatedly, it produces arcing and electrical noise. This noise can enter the high impedance RC timing node through capacitive coupling and cause the transistor to trigger earlier than normal. The example is like Ghost Touch on our smartphone screen. A touch screen uses capacitive sensing, so EMI can disturb the sensing area and make the phone detect a touch even when no finger is touching the screen. This false signal may cause wrong operation, such as opening an app, pressing a button, or moving on the screen by itself. This is similar to our project, where the noise from the chattering relay causes false triggering in the stable multivibrator circuit. So, how to reduce this problem? Since voltage is directly proportional to impedance, we lower the resistor value from 100 kiloohms to 10 kiloohms to lower the impedance value of the RC timing node. So the same noise current will produce a smaller voltage spike. At the same time, we increase the capacitor value from 10 microfarad to 100 microfarad. To make the node voltage is harder to change quickly because more charge is needed. The RC timing remains the same, but the circuit becomes less sensitive to noise. And finally, the circuit is tested again using the new R and C value. So we can see after mitigation, even when the chattering relay is placed near to the circuit, the LED flashing becomes more stable because the EMI effect reduced compared to before mitigation. Therefore, this mitigation helps electronic devices reduce false triggering in noisy environment.